This presentation presents the missing rotation angle of Rodrigues' rotation equation. Well, back in 1840 is when Rodrigues came out with his equation, and he was primarily interested in the orientation of a vector that is rotated about an axis by an angle. And his equation solved that problem, and that equation is used extensively in engineering in various other places. It's in attitude kinematics, but it doesn't have the rotation about the vector axis itself, which really comes out about more than a century later in 1952, and that's when Ishlinsky published his solid angle theorem, and that is what generates the rotation about the vector axis itself. It turns out that the rotation of Rodrigues' equation is the same as the rotation of the Earth with a vertical axis on the Earth. So a person standing on the Earth is moving according to Rodrigues' rotation formula, and he's also rotating about his axis, because people, when they're standing on the surface of the Earth, they're basically a vertical axis, and they rotate due to the spin of the Earth. So the kinematics is the same as Rodrigues' kinematics. Here's what Rodrigues' equation looks like. You have a vector, and it rotates to a vector v sub r, and after a rotation lambda about an axis, and he doesn't include the rotation psi about the vector axis itself. And the rotation is pretty much the same as the Earth's rotation. For a vertical axis on the Earth's rotation, it's exactly the same, but the motion is caused by the spin of the Earth. And again, the vertical axis would have a spin psi about its axis based on the missing angle that I'm going to present. So right down here we see equation 1. That's the final orientation of a vector, and it's not linked to a coordinate system, which is nice. Just uses the dot product and the cross product of vectors, and E is the vector axis of the rotation, the vector rotation axis, and lambda is the rotation angle. Now the origin of the missing angle, as I said before, is primarily the solid angle enclosed as the vector slews. So the vector slewing motion encloses a solid angle, and that solid angle produces a rotation. There's also an angular rate component to it that also gets added in. So if you have a vector located, pointing aligned with the rotation axis, then the rotation vector will rotate with the rotation axis, so then psi will be equal to lambda, because lambda is the rotation about the axis, and psi is the rotation about the vector. And so if the rotation about the axis is a complete rotation of 2 pi, then the rotation psi will be 2 pi also for any latitude on the Earth, for example, which may not be known by many people. So here's what the situation. We're looking down the axis, basically the North Pole of the Earth as it's spinning. If you're on the Earth, you'll move from A to B along a constant latitude trajectory, and the solid angle enclosed by a geocentric arc and the constant latitude arc is the solid angle we're talking about. That solid angle is equal to a rotation component about the vector axis. So when the vector goes from A to B, when it gets to B, it will have rotated by angle psi equal to that solid angle plus the an angular rate component that gets added to it. So when you add these two components, you come up with an equation, and the equation simplifies to equation number 2, which involves the tangents of the half angles, which is kind of interesting. And then since it's an analytical expression, you can take the derivative very easily, differentiate, and you can get the rate of change of that angle as a function of the rotation angle. So it really enables you to compute both the rotation angle and its rate, and you can relate it to the rotation of the Earth or the rotation of lambda. You can sort of a rotation factor of how much it's rotating about the axis versus how much it's rotating about the original axis, the rotation axis. So here's some numerical examples that were originally used for the mounting fixture for a Foucault pendulum. And you can see for various latitudes, 30, 45, and 60-degree latitudes, the rotation angles can vary up to 360. So there's various angles, rotation angles about the vector axis that occur that you can compute with those formulas. And these angles were never presented with Rodrigues' rotational formula. And you'll notice that when at 180 degree rotation, the rotation about the vector axis is also 180 degrees, and the same is true for 360 degrees. The vector axis is 360 degrees, so that's an interesting result there. And then for continuous rotation angle, we can see how the angle varies. In this case, the latitude is 15 degrees, so it's a nonlinear curve, so you can see how for the Earth rotation angle, the missing angle about the vector axis is the black line, and that is highly nonlinear. And on the second chart, the rate of the angle about the vector axis is on, and you can see that that's even greater than the Earth rotation rate. It's almost up to 4 times the Earth rotation rate when you're near 180 degrees. Each case, when you're near 180 degrees, that's when the rate is largest. And of course, when you integrate the rate over the whole 360 degrees, you're going to get 360 degrees, because no matter where you are, you're winding up at a rotation of 360 degrees. And here's one for 30 degrees, so it shows you if it's 30 degrees rather than 15 degrees of latitude, it smooths out a little bit and it's not as nonlinear. But you still get a maximum of 2. Since it's 30 degrees, you get a peak of rate of twice the Earth rate at 180 degrees. So that's actually spinning faster and about the vector axis. So that's basically what I wanted to present, and it gives you the analytic equation for both the rotation angle about the vector axis and the rate of that rotation. And hopefully, when other people publish the Rodrigues rotation formula, they may include the rotation about the vector axis itself, because it's always included in there, because the rotation depends on the trajectory and the enclosed solid angle. And if you're moving at a constant latitude, there is a solid angle you have to add in there. And so it definitely exists as a rotation about the vector axis. Should be included. And so anyway, I hope you enjoy this, and thanks a lot for watching.